Distance. In this video I'm going to explain to you how to calculate the distance between these two curves. Y is x squared and y is minus x minus 2 squared minus 1/2. Okay, if you make a picture of that, you get this green curve and this blue curve. Now if you want to know the distance between these two curves, it actually means the following. You take any green point and any blue point, you calculate the distance. And from all these possible pairs, you're going to look like what is the shortest distance. It turns out that there's exactly one green point and exactly one blue point, and between these 2 points, the distance is the shortest. Okay, so let's call this one point A and the other point B. If you don't have the line from A to B, then what you can do is look at the tangent line of the curve to A. My claim is that the line from A to B is perpendicular to the yellow line, to the tangent line. And why should that be? Why does that have to be the case? I mean, we sometimes use this, but why is this really true? And let's zoom out a bit. Let's say that you have, this is the yellow line here, this one is the tangent line, and that this blue line, suppose that this blue line is the line between A and B. So like somewhere here you have A and somewhere here you have B. Well, what you can do is then draw a line from here which is perpendicular to this yellow line, which is this line here. And then the claim is actually that this line here is shorter. The distance from here to here is shorter than the distance from here to here. Well, and this one is 90 degrees. So that means that you didn't have the shortest distance between these 2 points. So if you don't have that this line from A to B is 90 degrees with the yellow line, with the tangent line at A, then you didn't pick an optimal line. You can make something which is shorter. Okay, so the same thing over here at B, this line will also be 90 degrees with respect to this curve. Okay. Now you could use this actually by saying something like that the tangent line here then has to be 90 degrees to this tangent line, so the product of these tangent lines has to be -1. That's something you could use, but there's something way more simple here. Well, because here this yellow line is perpendicular to the line AB, and this yellow line is too, but it actually means that this yellow line here is parallel to this yellow line. Okay. So this means that the slope of the green curve at A is the same as the slope of the blue curve at B. So we can actually abuse this, for we now know that if we have the point A, so let's say that we have A is A comma A square, because that's what it is. Let's make the line a little less thick. And if point B is then B comma, well, and then you have to substitute this here. Then at x is A, the slope has to be the same as at x is B as this one. So if you calculate the slope for this function, the first one has slope 2x. The second function has slope -2 x minus 2. So this here actually is at the point A, so the slope here is 2a. And here it's at x is equal to b, so the slope here is -2b minus 2. And apparently they have to be equal. So now we can do a short calculation, and I'm going to do all the calculations in this video slowly. So this is then what you have. Now we can, for example, express a into b. What I'm going to do is express b into a. So I'm going to move 2b to this side. I'm going to move then 2a to the other side. And now I'm going to divide by 2. And I will get what b is. So b is equal to 2 minus a. Very nice. Okay. So now that we have b is 2 minus a, we can actually substitute it into b and express the point b in the value a. So this here is 2 minus a. And then here you have minus b minus 2. So b is 2 minus a, so you subtract 2 from that, so you get this. Minus a square minus 1/2. And let's simplify this a little bit more. 2 minus a is already as simple as it can get. Here minus a squared is just a square, so this becomes in total minus a square minus 1/2. Okay. So this is b, and this is a. So what we can now do is put the formula for the distance between a and b. So we can write down like, what is a, b, the distance from a to b. Well, what you have to make then is the vector from a to b, which will be actually the coordinates of a minus b. So what you will be getting is this vector for the first coordinate a minus this minus 2 minus a. That's the first coordinate. And then second coordinate will be a square. It will be this part here, in which we subtract that part, minus a square minus 1/2. Okay, so that's the vector, and that vector we have to take the length of. Okay, so this is actually everything I need at the moment. So if we want to take the length of a vector, what you have to do is take the square root of the first component squared. And you know what? I shall first simplify that vector a little bit more. So it's actually 2a minus 2. And here it's 2a square minus 1/2 plus 1/2. So that's what it is. Okay. So now we have to square this one. And we have to add the square of the other components. Excellent. Let me now zoom out a bit more, because then the writing becomes a bit nicer. Okay, so we have this equation here. And what we want to do is we want to minimize the distance from a to b. So we want to find the value of a such that this becomes as small as possible. Well, we can minimize this square root of this function, but it's actually okay to also just minimize the square of it. So that's slightly easier. It's not wrong if you start minimizing the square root of this function, but the calculations will be more complicated. So to find the value a, we have to minimize this function over here. So which actually means that we have to figure out the derivative of this function. Now there's two ways to go. You can either first expand this function, or you can take the derivative and then expand. So I'm going to do the latter. It's not wrong if you first expand and then take the derivative. That's perfectly fine. So we have this function. Let's give it a name. let's say it's f of a. So let's calculate the derivative to a. So what you get is 2 times, and then the derivative of the thing inside, which is 2, and then this not to the power 2 but to the power 1. This first 2 comes from this exponent which gets in front. The second 2 here comes from the derivative of 2a minus 2, and then you have 2a minus 2 to the power 2 minus 1. So now we're going to do the same thing over here. So we get a 2 from the exponent, then we get the derivative of the inside function, and that's going to be 4a. The derivative of 2a squared plus 1/2 is 4a plus 0. And then times 2a squared plus 1/2, and then to the power 2 minus 1, which is just to the power 1. So it's this. Very nice. So now we can expand everything here. So this is 4 times this value here. So that's 8a minus 8. And now this is 8a, and we have to multiply it with this one here. So we get 16a squared, or 8 to the power 3, I mean. And this is 8 times 1/2, so that's plus 4a. So we can simplify it a little bit more. We get 16a to the power 3 plus 12a minus 8. Okay, so this equation we want to put equal to 0, because we want to figure out where the function f is minimal. So we need to calculate the derivative of this one. Notice that this function here will have somewhere a minimum. It has to be, because this is sum of 2 squares. Okay, so now what we can do is try to find a solution to this one being equal to 0. So that's a tricky one, because in general, like a third degree equation is kind of hard to solve. But this one actually has a very nice solution, because you can, a is 1/2. Just check what happens. a to the power 3 is 1/8. So this first thing is 16 times 1/8, so that's 2. This here is 2 times 1/2, so that's 6. Minus 8. 2 plus 6 minus 8 is 0. a is 1/2 is a root of this equation here, and that's actually the only root here, and so this will be the minimum of this particular equation. Okay, now that you found a is 1/2, you can actually solve everything. For example, what you can do is you can substitute it into this equation here to find the minimal distance, which was the question. So what we can do is we can take AB is the square root of the function fa. Let's substitute 1/2 in here. So this becomes 1 minus 2. So this is minus 1 squared. Here you have a squared, so that's 1/4. So 2 times 1/4 is 1/2, plus 1/2 is actually 1. So then this gives you the square root of 2. So the minimal distance is square root of 2, and that will answer the question. If we want to, we can also calculate the coordinates of a. So let's go a little bit up, because we can substitute 1/2 in here, and we can substitute 1/2 in here, and then we get our coordinates. So a will actually be 1/2, 1/4. It will be that point. B, well, we have to figure out what is b. B is 2 minus a, which will then be 2 minus 1/2. So that's 3/2. So the value b is actually 3/2. And here you have this b is b minus 2. 3/2 minus 2. So that's minus 1/2. we square it, minus 1/2. So slight calculation will yield the result. This is 3/2. Minus 1/2 squared is 1/4. And you subtract it, but here you get 1/2 down from this. So it's 1/4 minus 1/2, so that's minus 3/4. Okay, let's check if that's correct. Yes, that seems to be the case. Okay, so the answer to the question will be this 1/2 square root of 2, because that's the distance. And here, if you want to, you also have the coordinates of A and B. And if you now go look back at the picture here, you see also like it's supposed to be somewhere like in this. It turns out to be exactly at x is 1/2 and then y is 1/4. And here it is exactly at 1.5. And if you use the GeoGebra applet on the page, you can see that if you really try to make the distance 2, then, or square root of 2, then you really need to have these two coordinates. Only then the distance is as low as it can be. Thank you very much for listening to this video.